M. Victor Anthony Raj. He has pursued his bachelor's, master's, and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idea Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series, BSc Physics Honors, Semester 6, Statistical Physics, Lecture 2. In this lecture, we are going to see Partition function, thermodynamic functions of finite number of energy levels, negative temperature, summary of all these concepts. Partition function. Partition function is a function used to explain the distribution of energy or partition of energy among the molecules of a thermodynamic system. To develop the concept of partition function, let us consider an assembly of ideal gas molecules obeying classical statics. You know, ideal gas molecules will obey ideal gas equation PV is equal to N RT. In that ideal gas, imagine that N1 molecule occupy the ith state with energy range between epsilon I and epsilon I plus d epsilon I and degeneracy Gi. This energy range is the energy of Ni molecule, Degeneracy is Gi. Degeneracy means the number of ways an energy level can be splitted is called as degeneracy. So, to learn the partition function, imagine that Ni molecule occupy the ith state. That ith state will be in the energy range epsilon I and epsilon I plus dAi with degeneracy dGi. Then from Maxwell-Boltzmann distribution law, that Ni is equal to Gi into e power minus alpha into e power minus epsilon I by kT. Here the exponential of minus alpha is a constant, then exponential of minus alpha minus epsilon I by kT is a factor which governs the occupation of Ni molecule in the ith state. This is what the Maxwell-Boltzmann distribution law says. Now, let us substitute e power minus alpha as A in the equation Ni is equal to Gi e power minus alpha e power minus epsilon I by kT. After substitution, that equation will become Ni is equal to Gi into A e power minus epsilon I by kT. This is how the Maxwell-Boltzmann distribution law changes after this substitution. Now, if the total number of gas molecules in the assembly is N, then this can be summed over to get the total number of gas molecule. So, capital N is equal to summation over I of Ni is equal to summation over I of Gi A e power minus epsilon I by kT. This is the Maxwell's-Boltzmann distribution law for n number of gas molecules. Now, this constant A can be taken out. This expression will change into A into summation over I G I e power minus epsilon I by k t. Keep this as equation 2. Now, from this equation 2, bring this A to the left hand side of the equation. So, left hand side of the equation will become n by A is equal to summation over I G I into e power minus epsilon I by k t. This component, this term can be called as Z. This Z is the Cartesian function. So, this quantity Z is called the Boltzmann Cartesian function or simply Cartesian function. We derive this Cartesian function from the concept of Maxwell-Boltzmann distribution, so that this Cartesian function is called as Boltzmann Cartesian function. In equation 3, we got that we understand that Z represents the sum of all the g I exponential of minus epsilon I by k t terms for every energy state of the given molecule. You know, in thermodynamics and quantum mechanics, a molecule energy level is a degenerate one. Degenerate one in the sense it can be splitted into many lines according to the state of the energy level. States of the energy level can be denoted by the quantum numbers of the energy level. So, if you know the quantum numbers of an energy level, you can calculate how many splitting that energy level will produce, or how many times that energy level is degenerate. All these things can be calculated if you know the quantum numbers of the state of the energy level. Like that, here the sum of all the terms g I exponential of minus epsilon I by k t gives the Z Cartesian function. So, Z indicates how the gas molecules of an assembly are distributed or partitioned among the various energy levels. This is how the Cartesian function can be learnt. Now, if the energy of the ith level is summation over I, the weight of the individual level is unity, then the Cartesian function can be written as Z is equal to summation over I exponential of minus epsilon I by k t. Keep this as equation 4. Here, the energy term in the Cartesian function not only contains the translational component, but also the other degrees of freedom like rotational component, vibrational component and electronic component. You know, in a physical system, these degrees of freedom are possible. So, state of a physical system can be represented by the number of degrees of freedom of the physical system, So, here this energy term in the Cartesian function not only contains the translational component, but also other degrees of freedom like rotational, vibration and electronic. And another important thing in statistical physics is a molecule energy is the sum of all its rotational, vibrational, translational energy. A molecule can rotate about its axis, then atoms in the molecule can vibrate, then electrons in the atom can transit, can jump from one energy level to another energy level. All these phenomena, all this activity will give energy. Sum of all these energy gives the total energy of the system. So, this is how the degrees of freedom can be related to the energy level. Now, let us come to the translation Cartesian function. In the earlier topic, we learnt that we learnt the definition of Cartesian function, and we learnt that that Cartesian function is not only due to translatory behavior of the system, but also due to the rotational, vibrational and electronic behavior. Here we will see how the translational Cartesian function can be obtained. The translational Cartesian function for a gas molecule can be derived as follows. Classically, gas molecule is a structureless identity, but we will assume that as a sphere, practically speaking, we can't fix any particular structure to the gas molecule. Then the number of energy levels in the momentum range P and P plus dP of the gas molecule is given by G of P dP is equal to V into 4 pi P square dP by H cube. This is the number of energy levels in the momentum range P and P plus dP. Therefore, the number of energy levels between energy epsilon plus dE is G of E dE is equal to V 4 pi 2 m epsilon by H cube into m d epsilon by square root of 2 m epsilon. These are the number of energy levels between the energy epsilon plus dE. This can be written like this also, that is G of epsilon into d epsilon is equal to 2 pi V by H cube into 2 m power 3 by 2 into epsilon power 1 by 2 d epsilon. Keep this as equation 5. So, this equation gives the number of energy levels. Earlier, the number of energy levels in the momentum range. Hence, the distribution of energy states is in continuation with equation 3 may be written as Cartesian function Z is equal to summation over I of G into exponential of minus epsilon I by k t, which is equal to integration between 0 to infinity G of epsilon d epsilon e power minus epsilon by k t, which is equal to integration between 0 to infinity 2 pi V over H cube into 2 m to the power 3 by 2 epsilon power 1 by 2 d epsilon into e power minus epsilon by k t. So, this is how the Cartesian function can be given in terms of the number of energy levels between the energy levels epsilon and epsilon plus d epsilon. In this integral, the definite integral can be shown to have the value integration between 0 to infinity of 1 by epsilon square into exponential of minus epsilon by k t is equal to root pi by 2 into k t power 3 by 2. So, this is the value of the definite integral exists in this. So, 0 to infinity e power 1 by 2 epsilon power 1 by 2 into e power minus epsilon by k t d epsilon. So, this alone will give the value root pi by 2 into k t power 3 by 2. Now, substitute this value in the Cartesian function. We will get the Cartesian function for a gas molecule as V by H cube into 2 pi m k t to the power 3 by 2. That is the Cartesian function for the gas molecule. That Cartesian function gives the translational Cartesian function. Like this, you can derive rotational Cartesian function, vibrational Cartesian function, electronic Cartesian function and so on. Next, we will see some thermodynamic functions a finite number by energy levels. Various thermodynamical functions and partition functions can be related. Thermodynamic function in the sense entropy, Helmholtz free energy, total energy, enthalpy, Gibbs potential, pressure of a gas, specific heat at constant volume. These are all various thermodynamic functions of a thermodynamic system or of a physical system. These thermodynamic functions can be derived in an elaborate manner, but here I am going to give only the final expression of these thermodynamical function in terms of partition function. Let us take entropy first. You know, entropy is an entity which measures the disorder, amount of disorder. So, S is equal to n k log z plus 3 by 2 n k. Here this z is the partition function, k is the Boltzmann constant, and n is the total number of molecules in a system. So, if you know all these quantities of a thermodynamic system, you can find the entropy of a system, which is a thermodynamic function. Then the next thing is Helmholtz free energy. This Helmholtz free energy is denoted by the letter F, and it can be calculated by the formula F is equal to n k T log z. The next thermodynamical function is total energy. This total energy is the sum of internal energy and the work done by the thermodynamic system. So, total energy E is equal to number of molecules in the system, that is n, into average energy per molecule, that is epsilon bar. This epsilon bar is the average energy per molecule, which is equal to n k T square into dou of log z by dou T at V is constant. So, this is the expression for total energy of a thermodynamic system. The next thermodynamical function is enthalpy, which is denoted by the letter H. H is equal to n k T square into partial differentiation of log of partition function with respect to temperature at constant volume plus R T. So, this is how enthalpy is calculated for a thermodynamic system. The next thing is Gibbs potential. Gibbs potential is G is equal to n k T square partial differentiation of log of Z with respect to the temperature at volume constant plus R T plus n k T by log Z minus 3 by 2 n k T. So, the Gibbs potential expression has 4 terms, n k T square, and that is one term, R T is the other term, then n k T log Z is the next term, 3 by 2 n k T. Here T is the temperature, K is the Boltzmann constant, then R is the universal gas constant, then n is the number of molecules in the system, Z is the partition function. So, if you know all these quantities, you can find the Gibbs potential of a particular thermodynamic system. The next thermodynamic function is pressure. Pressure of a thermodynamic function P is equal to n k T partial differentiation of log of Z with respect to temperature at constant temperature. The last one is specific heat at constant volume. Specific heat at constant pressure is also possible, but here we are concentrating in specific heat at constant volume, that is C suffix V is equal to n k into 2 T into partial differentiation of log of the partition function with respect to temperature plus double derivative of the log of Z with respect to volume into T square at constant volume. This is the specific heat capacity at constant volume in terms of partition function. So, here in this topic we learnt how to write the expression for various thermodynamic functions of a physical system in terms of partition function. Then the next concept is negative temperature. You know positive temperature. What is mean negative temperature? To understand the negative temperature, you must know the definition of temperature from the entropy versus energy relationship. Let us look into the entropy energy curve. The slope of this entropy energy curve gives the reciprocal of the slope of the entropy energy curve gives the temperature. This is how temperature is defined in the entropy energy curve. In equation in mathematics, this is expressed as 1 by T is equal to partial differentiation of entropy with respect to energy when the volume and number of molecules are constant. But we know that the total energy is equal to N into epsilon, where epsilon is the energy of each molecule, then N is the number of molecule. So, E is equal to N epsilon. Substitute that we will get 1 by T is equal to minus K by epsilon dou by dou N of N plus log of N plus by N plus N minus N log N minus by N. Here this N plus and N minus has got some definition. The definition of that N plus and N minus is given like this, that is N plus is equal to 1 by 2 into N plus N, and N minus is equal to 1 by 2 into capital N minus N. This is how that N plus and N minus is defined. By substituting these two in the relation 1 by T, we get 1 by T is equal to minus K by epsilon dou by dou N of 1 by 2 capital N plus small n, where capital N is the number of molecules in the thermodynamic system and small n is the state of a thermodynamic system, into log of 1 by 2 into N plus N by N plus 1 by 2 into capital N minus small n into log of 1 by 2 into N plus N by N. This is how the expression for inverse of temperature or reciprocal of temperature can be obtained in terms of the total number of molecules. By simplifying this, we will get the 1 by T, that is inverse of temperature, as 1 by 2 into K by epsilon log of N minus N by N plus N, which is further equal to 1 by 2 K epsilon log of N minus by N plus. So, this is the final expression for the reciprocal of the temperature. At the conventional absolute zero temperature, that small n is equal to N plus minus N minus, which is equal to 0 minus N or minus N, which is lesser than or equal to 0. A negative value of N is known as lesser than 0 or equal to 1. Therefore, when T is equal to plus 0, that is at absolute zero temperature, and entropy is equal to 0 at E is equal to minus NE. This is how the temperature energy can be learnt. At 0 temperature, that is at 0 Kelvin, entropy is 0 and E is equal to minus NE. As the temperature is raised, energy is supplied to the system, then particles jumps from energy state epsilon minus to epsilon plus, where this epsilon minus can be imagined as a ground state energy level, and epsilon plus can be assumed as excited state energy level. You know, in a physical system, if you supply an energy to a system, molecules present in the ground state energy level will automatically jump to the excited level. That is what happening here, as they say. So, upper level glows at temperature greater than 0 till we have n is equal to 0, giving probability S dash is equal to n k log of 2, a state of maximum disorder. So, maximum disorder means entropy will be maximum and temperature is equal to plus infinity. As we learnt in the definition of entropy, if we supply heat energy, temperature increases, disorder increases, so entropy increases. That is what they say here. A state of maximum disorder will be obtained as S dash is equal to n k log of 2. Energy supplied more, so upper energy level becomes more populated than the lower energy level, that is number of atoms in the upper energy level which is denoted by n plus is greater than the number of atoms in the lower energy level, and so n is greater than or equal to 0 and we get a decrease in entropy. So, and temperature becomes lesser than 0. Thus, the system loses its normal behavior. When the system loses its normal behavior, the negative temperature will come into play. So, that is what equationally it is denoted as T is lesser than 0. We get a decrease in entropy. The decrease in entropy is obtained when the upper level becomes more populated. When that upper level becomes more populated, when the energy is supplied to the ground energy level. Thus, the negative temperature T minus corresponds to higher energy than positive temperature T plus. So, for a system to have negative temperature, the following conditions must be satisfied. That is, the system must have a finite upper limit to the energy spectrum, then the system must be in thermal equilibrium. Thermal equilibrium in the sense its temperature must be equal to its surrounding temperature. That is the meaning of thermal equilibrium. So, to get a negative temperature, the system must be in thermal equilibrium. Then the system must have the negative temperature states isolated from positive temperature states. These are all the conditions a thermodynamical system must satisfy to get the negative temperature. So, negative temperature corresponds to higher energy state than positive energy state. This is what we learnt from the negative temperature. From this lecture, we learnt about partition function, thermodynamic functions and negative temperature. Partition function shows how a gas molecule partitioned or splits its energy supplied. This partition function is applicable for all degrees of freedom like translatory degrees of freedom, rotational degrees of freedom, vibrational, electronic. These are all some of the examples of degrees of freedom. This partition function is applicable to all the degrees of freedom. Then calculation of thermodynamical function for a system. Some of the thermodynamic functions are entropy, Helmholtz free energy, total energy, enthalpy, Gibbs function, pressure of a gas, specific heat at constant volume. These are all some of the thermodynamic functions. We learnt the mathematical expression for all these thermodynamic functions. Then we learnt about negative temperature, where negative temperature corresponds to higher energy level than positive temperatures. After listening to this lecture, you can answer the following questions. Define partition function of thermodynamical system, define enthalpy of a system, express pressure of a gas in terms of partition function. Thank you.